Let's take a look at an example problem for Module 7.2 for ME12 Dynamics course. In this example problem, we're told that we have two 0.4 kilogram masses with initial velocities given to us as 2 meters per second, and that these experience a moment of 0.6 Newton meter. They ask us to find the speed of the blocks A and B when our time is equal to 0.3 seconds. So we can see we have our given diagram over here. We have our mass A on this side, our mass B on this side. We know that those are both identical and have a mass of 0.4 kilograms. We have our moment shown here about our axis from C to D of 0.6 Newton meters. And we have our distance from the center of this axis out to block A and block B of 0.3 meters. So our plan to solve this problem is to apply the principle of angular impulse and momentum. Since velocity of A and B remain equal to each other at all times, the two momentum terms can be multiplied by 2 as well. So now that we've looked through the problem statement, understand what they've given us in both the wording and the diagram, what they're asking us to solve for, our next step is to create our setup page here. So in the setup page here, I redraw a simplified 2D version of the diagram here. Again, I have the center axis from C to D. I have these two masses, equal distance from the center axis, mass A and mass B, a distance of 0.3 meters away from the center axis, and my moment of 0.6 Newton meters about that center axis there. Write out all my givens. My mass A was given to me as 0.4 kilograms. My mass B is also 0.4 kilograms. My velocity of A is equal to my velocity of B, which they give us as 2 meters per second. My moment was given to me as 0.6 Newton meters, and that distance from the center axis to the masses is 0.3 meters. And I want to find my velocity of A and my velocity of B when our time is at 3 seconds. So now as we begin our solution here, we want to take a look here and realize that our h0 or h0 are our initial and our final angular momentum, and these h0 values or angular momentum values are defined as the moment of the linear momentum of a particle given by this expression here, mv, in our case for this problem, our d here. So now we want to jump to our principle of angular impulse momentum for a system of particles, and we have this general equation that we have boxed here. So the summation of our h0 plus the integral from t1 to t2 of m dt is equal to the summation of h naught d2, and this comes from equation 1520 in our textbook for this general expression right here. So from this here, we can then start plugging in for our known values. So we start with our h0 expression. We recall this relationship up here, so we can plug this in here, summation of those, so we have it for A and for B, for mass A and for mass B, we still have that MVD. So I label these out MA1, VA1, DA1 plus MB1, VB1, and DB1 for the summation of those right there. So this now leads to this expression to replace this guy here for our summation. Then we have our integral here from t1 to t2 of our m dt. So we're just going to leave that as it is for now. And then we go to the right-hand side of our problem over here for h02 here. So this is our, again, summation for mass A and for mass B here. And now this is at MA2, VA2, DA2 plus MB2, VB2, DB2 here. For our right-hand side of the equation now becomes this guy here for our summation. Plug in our known values, our MA1 and our MB1 and MA2 and MB2 are all 0.4 kilograms. So we can plug those all directly in. Our VA1 is given to us as 2. Our VB1 is 2 as well. Our velocities are the same. And that diameter, the distance away from the center axis, is also the same, which is our 0.3. So we can plug those values in there and there. We don't know our VA2 or our VB2, but we know they're equal to each other, and we know that distance doesn't change. That stays at 0.3 for both of those. So if VA2 is equal to VB2, we're going to call this now our V2. Now we can plug and chug, put these all in, simplify this down. Left-hand side before our integral is 0.48 plus our integral from t1 to t2 of m dt is equal to, we got our math here, 0.12 v2 plus 0.12 v2, or simplify that down to 0.24 when we add those two together, v2 right there. So now we have our 0.48 plus our integral from t1 to t2 of m dt is equal to 0.24 V2. So as we continue on here with our solution, we recall what we had in the bottom of our last slide here. We rewrite this down here. And now what we want to do is deal with our middle term here, our moment. We realize our moment was given to us as 0.6. So we can plug that in here, and what we end up with is 0.48 plus the integral from t1 to t2 of our 0.6 dt is equal to 0.24 v2. So now what we can do is we realize that our t1 and our t2 were given to us in the problem statement. That's from 0 to 3. Our m, our 0.6 is a constant. We can pull that out from the integration. What we end up with is 0.48 plus 0.6 times integral from 0 to 3 dt is equal to 0.24 v2. From there, we can do out our integration here. Integral of dt simply becomes t, so we end up with 0.48 times 0.6 times our t value evaluated from 0 to 3 is equal to 0.24 v2. Do out those limits there, and we end up with 0.48 times 0.6 times 3 is equal to 0.24 v2. Our only unknown in this case here is our v2, but let's rearrange and simplify. Our 0.6 times our 0.3 becomes 1.8, so we have 0.48 plus 1.8 is equal to 0.24 v2. Simplify down a little bit more. 2.2 is equal to 0.24 v2. Solve for our v2. v2 is 2.28 over 0.24, or our v2 is equal to 9.5 meters per second right there. We know that our va2 is equal to vb2, which is exactly what we called our v2 here. Those are both equal. We've got the same velocity. This is equal to our 9.5 meters per second.